guys. Welcome to the Chemistry 2041B review. I understand if you guys aren't here for Chemistry 2041B, you're probably in the wrong room and we can redirect you somewhere else. If you just want to study in here, that's fine as well. I won't mind, as long as you don't make a lot of noise and aggravate us the entire time. Pretty much, I'm going to be going over everything you need for ACS finals as well as Hernandez type stuff because he teaches different material. I'll be going over pretty much from beginning to end, separating it based on the typical groups the ACS does. It's a good review for any of the classes pretty much overall. So another thing I want to mention to you guys is for studying, I really do recommend that you study the ACS book itself. I mean, you're taking a test based on the ACS, so if you haven't gotten it, yeah, get it from a friend by now. Another thing is the ACS seems very daunting at first. I know when I took it that I was really afraid of the exam. However, the fact remains that it's actually quite easy compared to what your teachers have on your tests. It's a lot less tricky questions, and it's pretty simplistic when it comes to actual answers. So even though if the ACS book looks really difficult, it's really not that bad in practice when you actually get it. A final note is online on the SARC WordPress site, I've posted how to work out all the things on the ACS book. So if you guys do not know how to work out a question, I worked it out for you from a previous year. Disclaimer, if I ever go over anything, it doesn't necessarily apply to your class because I did it a year ago, so things change over time. But I still want to go over that with you guys as an additional resource. You can always view this now, and it's going to be streamed, so you guys can check it out later on YouTube as well in case you forget anything or need any extra assistance. All right, guys? So I guess from here, we can start talking about actual chemistry. Woo. Jazz hands, guys. So here's my review. Yeah, to all my tutees, first of all, thank you for the great year. I know some of you are just awesome. And let's start. I have a lot of puns. My puns are punishments, so sorry. I think you lost an electron, but I'm not positive. So let's start with the first one. What type of shape would the 3d orbital be in nickel? So whenever we're doing atomic shapes, right, of orbitals, we pretty much know that there's really only a couple shapes that you need to remember. So when it comes to S, you have a circle. So S would be a circle shape. Can you guys see that, by the way? OK. S is a circle shape. We have this. This is what a p orbital looks like. It looks kind of like a peanut. So P for peanut, S for sphere. And D looks like a four-leaf clover. Or a butterfly, I guess you can call it. So when I'm asking what would the shape of the 3d orbital in nickel be, I'm pretty much asking you what does a typical d orbital look like. So that would be a four-leaf clover. Right. Number questions. Which has the shortest wavelength? So if you guys remember at the beginning of the year, you learned about wavelengths, frequencies, things like this. Number 2 is asking us what the Bohr model is. If you guys don't remember what the Bohr model is, it's when we took this right here as an atom, and we had levels above it. So n equals 1, with n equals 2 being slightly close together, n equals 3 being even closer together, and n equals 4 being really close. As you go up each level, it's actually going to decrease the distance between each n compared to where the atom is located. So what I'm asking is, which has the shortest wavelength? Now, if you guys remember, wavelength, frequency, and energy are all interrelated with each other. So frequency, as energy increases, frequency also increases, and wavelength goes down, right? And we have to remember that the distance between each one going up is actually smaller. Finally, the more you fall, the electron from a top level to a bottom, the more energy is going to be released. So pretty much we're asking which one releases the most amount of energy. The answer to that would be whatever falls from the top to the bottom the most. So let's look at a couple of these answers. Now, 6 to 3 is actually a very small distance, even though it looks like it went 3 different rows. B is 2 to 1, so that would be approximately here. C would be 3 to 1. So we already know that C covered a bigger distance than B did. So we can eliminate B. We also know that if we look at C, we have 3 to 1. And finally, D, we have 8 to 7. Now, 8 and 7 look like big numbers, but remember, the further you go up, the shorter the distance between each n. So we can eliminate D as well, since it's such a short distance. So my question is, A and C also, they both go through 3. However, as you go towards the center, like I said, it's a bigger distance. So C fell the most. Whatever falls the most releases the most amount of energy. So, wait, did I write the wrong answer on this? so anyway, we have, wait, I just marked this out. This is the right answer, I'm sorry. So 8 to 7 is the smallest distance. Smallest distance means it has the shortest wavelength. The reason is shorter wavelength means low energy amounts. It means that this is going to, frequency as well goes down. So when we have something like this is going to release a lot of energy. But if we have something like this is going to release a very low amount of energy. Low energy means it's going to be low frequency and high wavelength. We're looking for the shortest wavelength, so we're looking for the one that has the most amount of energy done. Guys, regardless of what I said on the review, it's not right. This is actually the answer of 3 to 1, right? I'm sorry about that. The reason is this has the highest amount, so ignore what it says on your sheet. Okay. Which are paramagnetic. So what does paramagnetic mean in the first place? Paramagnetic is whenever you have something that has electrons that are not actually filling the entire octet, right? So when we draw out the electron configuration for like Br minus, Fe minus, and Na plus, we're looking for if the actual orbital is full or not. So if you guys remember how you do electron configuration, you start with the S at the bottom, 1s, then you fill it, then 2s, you fill it, and so on and so forth, right? So what I'm asking is, which of the following is paramagnetic? If you look at Br, Br has one more electron necessary to fill its octet. This is going to fill it completely, meaning it has the full octet of electrons, making it look like Kr. Kr is diamagnetic. It has all of its electron outer shell full. Fe negative, well, we don't really necessarily know, but we could draw that out, right? Fe negative is going to be what? It's going to be Ar along with 4s2, and then 1, 2, 3, 4, 5, 6, 3d, 7. And the reason why I put 7 versus 6 is because it's -1. The D block is not completely full, so we know that 2 is an answer. So we know that Fe minus is not full, so that's one of our answers. Na plus is the same thing as saying Ne, and Ne is a noble gas. Noble gases have a full octet. So we know that that can't be an answer. And being that there's only, every response has 2 answers, we know that the answer has to be C. And Mg, if you look on your periodic table, has a 2s. That's, well, I should have wrote up here. I think that cut off when I printed it on the PDF. But that's supposed to be Mg plus. But it's, would look like that as plus. Yet again, my stupid printing error forgot this part, so. I put this on a PDF the other day, and then it's kind of screwed up with printing. A certain atom has 5 p orbitals. What is the outermost d orbital for this atom? So if you look on your periodic table and you go to the 5th p orbital, so this is from an ACS book, we go from 1p orbital, 2p orbitals, 3, 4, and 5. So it's going to be some type of element in this area. So if element's in that area, what type of d orbital is it going to have? It's going to be in this d, is going to be its last d. So if we know this is the 3d, this is the 4d, and this is the 5d, it's going to end up with some type of phi d orbital as its outermost orbital. So this would be d as an answer, if you guys can see that. Okay. 3 was C, and that was an Mg+, not just an Mg. Okay. Next, we're just going to go over 5, element with the electron configuration like that. We know that 1s2, 2s2, and etc. This ends at the 4d. This is all a noble gas. This is 3d5, 4s2, which is the equivalent of manganese. If you look on your periodic table, it goes over 3d, 1, 2, 3, 4, 5. So that's how we know it's manganese. Which is not isoelectronic. To figure this out, we need to know the amount of electrons in each one. Br- has 36, if you look at your periodic table, because 35 plus 1. Se has 34 plus 1, so that's 35. As2, -2, is 35 as well. It is 33 plus 2, because 2 extra electrons. And Ge is 32 plus 3, which is 35. From this, we can tell that A is not isoelectronic. Isoelectronic meaning what has a different amount of electrons compared to everything else. So let's go on to 7. Did I skip 6? Oh, 6 was A. It was the Br-. Determine the number of protons and electrons in this ion. So Ag plus 2 has 47 protons, right? We have 47 protons. That means we have 47 electrons typically. However, because it's plus 2, we're going to subtract 2 electrons, which is going to equal 45. Does that make sense, guys? Next, let's go over other answers. Which is inorganic? So, to be inorganic, something has to have lacking a C. So organic means it has a carbon inside it. I know that water looks like it's actually organic because it's used in so many different reactions in life. However, water itself is not organic. It does not contain a C. To be organic, something needs a C molecule, making all of these organic. A is the answer to this one. Which elements are most similar? So on the periodic table, we have certain trends. Every single line of the periodic table, known as a period, and every period deals with atoms that have very specific properties that are very similar. For example, if we look at this periodic table, and we see Cu and Ag and Au, copper, silver, and gold, those are very common. You guys probably know what each of these three look like. They're very metallic, they look alike, they're very strong, they're pretty for jewelry. So taking into account that every line of the periodic table, each period, is very similar in its properties, which elements are most similar? So really, we're looking through the periodic table to see which ones are in the same line of the periodic table. So we have Au and Hg. Au is right over here, and Hg is over here, which is in a different row. Sorry. Au is in a different row from Hg. So these are not going to be similar in properties. We then have O and Te. Oxygen is over here on the periodic table, and Te is over here. These are both in the same row. So even though you don't really think of O and Te being similar, being that they're in the same row, they have very similar properties and act very similar in nature. Ca versus K. Ca and K, potassium and calcium, are in different rows of the periodic table. Because they're in different rows, we know that they're not necessarily similar with their properties. Finally, we need to look at H and Ne. H is on the top left corner of the periodic table. Ne is in the top right part of the periodic table. These are not in the same period. These are not similar at all. The reason why we say things in the same period have similar properties is because the electrons in their outermost layer are pretty much exactly the same for each species. So the amount of electrons in the outermost shell of Ne is very similar to Ar. They both have 8. F and Cl act the same in nature because both have 7 electrons in their outermost shell. And this makes them both very reactive, wanting to gain that extra electron. So that's why each period is very similar to each other. Yes, you look at the period, not the group. The period is up and down. Sorry, the period side to side. I'm sorry, I've been saying period. Period is like this. And group is up and down. I'm sorry, I've been saying it wrong. Group. You look at the group number. Sorry, you write your periods like this. That's at least how I remember it. What? Yes, if you go to the SARC WordPress site for UCF and go to chemistry, this is located under it. Periods are, when you write dot, dot, dots, you write them side to side. So this would be a period. Period 1 would be like H and HE. Number 2 would be LI, BE, BC, NO, F, NE. So yeah. I have another question about what's diatomic versus not. So we have ONIS. To determine if something is diatomic, like we said before, we need to figure out which one has electrons that are not filling. So first of all, guys, what does diatomic mean? Let's just write it that way. Diatomic means that we have a molecule in nature that comes in twos. So what happens is it's most stable when it's actually 2 together versus 1. So if we look at the periodic table, there's this fancy way of remembering this. It's phone line. So phone line is P-H-O-N and then line. What does this mean? So F is this one. This is diatomic. H is diatomic up here. O is diatomic. N is diatomic. And the entire line right here is diatomic as well. So phone line, P-H-O-N, and this line, represents all the diatomic molecules on the periodic table. Now, there are polyatomic ions, so those involve multiple, and that's not what I'm asking for in the question. So pay attention to the fact that polyatomic ions, I'm sure you guys are very familiar with, would be if you get multiple ions, multiple things together like SO4 or PO4, -3, things like that. So by asking for diatomic, I'm asking which one of these am I having in this, which one is not diatomic in my question. So let's look at the answer choices. O-N-I-S. So O is right here, and it's part of phone line, so that's not the answer. N is in the phone line, like I stated. And what are the other ones I had? I is in the line. You can see it right over here. And the last one, sulfur, is not diatomic. Sulfur itself is usually involved in polyatomic ions. So sulfur would be the answer on what is not diatomic. Okay? Next, let's move on. So this is actually my favorite section. Molecular structures and bonding. What do I do when all the good mates are gone? Ha ha ha. So which Lewis structure is correct for CO? Hopefully you guys know how to draw Lewis structures by now. So CO, I'm going to draw it over here on the left. So we're going to draw C first, and we're going to draw O next. I can't see it on that page. So let's draw it on here. So let's draw CO. So we have C, right? Can you guys see that at all? Okay, C. It's kind of blurry. Okay, there you go. C has 4 electrons in its outermost. O has how many? 1, 2, 3, 4, 5, 6. So pretty much we need to start bonding these electrons together, right? So we have this, which can go here. We have this that can go here, right? Now, we have an issue, guys, right? This right here, this is not OK, right? We have a C that only has 2, 4, 6 electrons, and we have an O that has 8. Now, this is an issue, right? We have to make sure that both have a full octet of electrons. So this is not the answer, even though it looks like it's really stable. C needs to have 8 electrons, and O has to have 8 electrons in order to be actual compound. So let's draw a different one over here. 4, 6. This is what CO actually looks like. So let's just make sure with our formal charges and things such as that. So does this actually have 8 electrons? 1, 2, 3, 4, 5, 6, 7, 8. So this has 8 electrons, so this one's good. This one, 2, 4, 6, 7, 8, it has 8 electrons. Now, I just want to go over formal charges really quickly. So to calculate formal charge, we need to add up all the lines, and we have to add up all the dots, and we have to subtract that from how many are typically found around it. So we have 1, 2, 3, 4, 5. So carbon typically has 4. There are actually 5. This is going to give it a formal charge of 1. And O typically has how many outer electrons? 6. So count the lines, 1, 2, 3, 4, 5. So there's 5 versus the typical 6. So that's going to be 1. So we have a plus and a minus 1. Together they cancel out to form 0. So this molecule can't exist. We want to usually optimize it so there's 0 charges instead of a positive 1 and a negative 1. However, in this case, as we saw over here, we can't make both 0 without one having some type of electron deficiency. So this is what our molecule looks like, CO. So let's look back at our question. So which Lewis structure is correct for CO? We have the only one with a triple bond are B and D. So it can't be A and it can't be C. Next question would be, is it going to be B or D? So let's look back at our structure to kind of see which one it looks like. So here's our structure down here. Does oxygen have 2 lone pairs? No, it has 1. The one with 2 lone pairs, one's unstable. So we know that B can't be the answer. But let's just make sure that D is right. So carbon has 1 lone pair, and oxygen has 1 lone pair. D is the correct answer. Now be careful, when it says lone pair, it means 2 electrons here as a pair. It's not talking about 1 individual electron. So next question. Dylan is looking for a BF, but he can't seem to find a guy who is stable. Can you help him find chemistry by choosing the most stable compound? I know, UCF has some unstable people. So we have BEF2, FBF2, BAF, and BEF3. This thing is being difficult when it comes to zooming. So we have, to understand this question, we need to know about whether something could fill its octet, whether it goes under its octet, etc. So BE typically has how many things attached to it in nature? BE can go under its octet. So what does this mean? BE needs 2 things attached to it, and that is considered a complete octet. Now, this is one of the only ones that actually defy its octet. Some of the other ones that defy their octet would include things such as B, which has 3 things attached to it. BE has 2. Some other ones would be AL, which has 3. Hydrogen has 1. So this means that hydrogen can only make one attachment, so 1 single bond. Aluminum can make 3, but no more. Boron can make 3, but no more. And Be can make 2, but no more, to be stable. So out of the choices here, BF2 is not stable because B needs to have 3 different things attached to it in order to be complete as an octet. BAF is not stable because BA is right here on the periodic table towards the bottom. It is +2. F is -1, so that would make it a +1 charge. +1 means that it's not very stable. Then we have BEF3. So BE, as I said before, wait, where am I located? BF, okay, so I'm right here, right? Okay, so we know that this one is unstable as well because BE follows the rule of 2. I don't know why this is being so fuzzy. Okay, so as we said before, BE needs 2. So this one's wrong, and this one's wrong. The only stable guy left is BEF2. Okay? So, put this over here. Sorry, guys. Okay. Where am I? Okay. 13. Dylan's going on a date. He needs to impress a guy with as much pi as possible. Find which molecule has the most pi bonds. So in order to figure out this question, we need to draw out every single one of those. So by now, I'm sure you guys know what CO2 looks like, right? Because they include it on like every single test. CO2. So CO2 has how many pi bonds? 2. The reason we know this is every double bond contains 1 pi bond and 1 sigma bond. We now have O2. So O2 looks like this. So that's 1 pi bond, so we know that this is not the right answer. Now we're going to go over CO3, negative 2. So CO3, negative 2 looks like C. Sorry. I'm going to draw it somewhere else. Here. So that's CO3, negative 2. We see once again that this has 1 pi bond, so this is not the answer. And the formal charges on this is this O is negative 1 and this O is negative 1 as well, in case you guys were curious. And the final one, CH2O, is this. And as we see, that only has 1 pi bond. So the answer has to be CO2. OK, guys? Let's go down a little. Dylan is finally building a bond with somebody, but he wants to make sure it's strong. Which bond is strongest? So if you only have CC, we have 1 sigma bond, right? If we have C double bond C, we actually have 1 sigma bond and 1 pi bond. So if we have more than just 1 sigma bond, an extra bond is going to make it stronger. This means that, let's look at C triple bond C. This has 1 sigma and 2 pi's. So we have another pi. So this means this one has 1 bond, this one has 2, and this one has 3. The more bonds you're adding, the stronger this molecule is going to be to keep this bond. The last one, CH, has only 1 sigma, making this one the strongest bond of the 4. So we can say that the bond that's strongest is the C triple bond.
Which bonds are stronger, sigma bonds or pi bonds?
Sigma bonds are stronger. So why this makes sense is it would be very difficult to break a molecule that's typically stabilized by 1. However, when it has 2 bonds, pi bonds are actually incredibly weak and can be removed pretty easily. So yeah. However, the more bonds you add, obviously, the stronger the molecule is going to be because you just have extra bonds. So IF4, what is the electronic and molecular geometry of this compound? So let's draw what IF4 looks like in the first place. We have I here, right? And we're going to have 4 different Fs. So these 4 Fs. And we're going to obviously have to bond these to this I. So we have 1, 2, 3, 4. Wait, how many does IF4? Gotta look at my periodic table for a second. OK. Did I forget a formal charge on this one too? 1, 2, 3, 4, 5, 6, 7. One second, guys. I think it's IF4 minus. So I want to show you guys this chart really quickly. I meant to write IF4 minus, but my minuses keep disappearing from my sheets for some reason. But what's important for you guys to know about electronic geometry and molecular geometry is this chart. If you guys, I believe Patino and Dixon's class both gave these out. The first line, the first lane of this on the complete left side represents the electronic geometry of different compounds, while the right represents all the different molecular geometries that something can adapt. So if we look back at this, it's supposed to be IF4 negative, but I think I got cut off again with my pluses and minuses. So this is supposed to look like an I with a this 1F, 2F, 3F, 4F, and then one more lone pair here. So it's IF4 negative, which is what shape? So This is square pyramidal. And it's also octahedral. But which is which? So electronic geometry is going to be this one. Why? So during electronic geometry, we're treating the electrons as if they are actual atoms. So if you notice on here, you see how each of these black dots represent different atoms attached. Electronic geometry is like saying that this atom is like an electron. However, molecular geometry is taking into account that these lone pairs are here. So answer for this one would have to be, so it's a square planar. Sorry, planar. Did I write pyramidal? I wrote pyramidal. Planar. I'm killing myself today, let's be honest. So, okay, so square planar. We have a lone pair up here, we have a lone pair down here, and then we have 4 things attached. Each of these attachments count as 1. So if you look back on your VSPR thing, we have this with 1, 2, 3, 4, 5, 6 different attachments. And we have also 2 lone pairs and 4 different attachments making square planar as well. So that one is square planar and octahedral, which is B. I wrote square planar middle for some reason, but I circled this. This is the right answer for 15. Dylan needs to get in shape or else he will cry, KRI4. What's the shape of KRI4? So KRI4 is going to look like a KR in the middle, right? With I's all the way around it. So we have to remember something, that if it's the 3rd row or past, an element can actually go over its octet. This is important to understand because things like Kr, even though they're noble gases, can bond to other things in these compounds. And it doesn't matter that they're over 8 electrons in their outermost shell, because you have to remember that they have a d orbital, and d orbitals can hold more. So let's start bonding these. So we have 1, 2, 3, 4, 5, 6, 7, 8. And all of these I's, of course, have electrons around them as well. So this Kr has 4 electrons, so 2 lone pairs, and it has 4 different bonds. So what is the shape of KRI4? What do you guys think? This is going to be square planar as well. It's going to be B. Is that the electronic geometry or is that the molecular geometry for this compound? It's molecular. So one more question for you guys really quickly. Is that molecule polar or nonpolar? This molecule is actually nonpolar. Now this is a really strange concept that I encountered on your ACS before. This lone pair is actually canceling out this lone pair because they're directly across from each other. If you guys remember, these are 90-degree angles from each other. So this is 180 from this, meaning that this one pulling this way is pulling exactly the same in the opposite direction. All of the I's are pulling directly away from each other too. This I pulling this way as much as this I is pulling, and this I pulling this way as much as this I is pulling. This molecule is actually considered nonpolar. I just thought that was a kind of cool thing to include. So next up, we have the electronic geometry of NH3. So NH3 looks like this, H, H, and H. So we have NH3. So what is the electronic geometry of NH3? So if you guys remember, electronic geometry is the first column of that VSEPR theory page. So this is going to be tetrahedral. It is not going to be trigonal pyramidal. Trigonal pyramidal is actually representing the molecular geometry of the compound. Okay? If Jacob and Bella had a baby, it would be a hybrid vampire werewolf. ICL5 and PCL6, if they were compounds and they had a baby, what type of hybridized orbitals do they have? So pretty much what I'm wondering is, what is the hybrid orbitals for ICL5 and PCL6? So ICL5 is going to look like an I with 5 different CLs attached. 1, 2, 3, 4, 5. So 5. This leaves a lone pair extra. So my question is, what what value is this? Is it sp3? Is it sp3d? Is it sp3d2? The answer to this is going to be D. Now, we first have one s, we have 1, 2, 3 p's, and we have 2 d's. So if you guys remember, s only has one orbital, p's have 3, and then d's have 5 different orbitals. So once we ran out of one s, we included p's until we ran out of p's, and then we include d's until we're done. This is why D is the right answer. So, comes to that, 18. So 19. Dylan was cut off while trying to drive to UCF today by a person who has no chill. NOCl has what type of molecular geometry? So let's draw NOCl first. So actually, I should have known. We have N, we have an O here, and we have a Cl. This O is getting a double bond. Sorry, ignore that. So my question for you guys is, what's the actual shape going to be of this? Did I draw this right? Yes, okay. So this molecule is going to be V-shaped / bent. The reason is this lone pair pushes everything else down out of the way, making this actually into a V shape. You can see this back on this page again, if you see V-shaped or bent as sp2. So bent, after all, he's all bent out of shape, not the other ones. Okay. So we have, quick, identify all the lone pairs in the entire compound so Dylan doesn't feel like he's the only lonely guy. XeOF4. So let's draw XeOF4. We have Xe. Let's draw one O and draw 4 Fs around it. So we have 1, 2, 3, 4, 5, 6. Okay. And these, of course, have electrons around them as well. The reason we know that is because oxygen needs a double bond in order to keep its formal charge as 0. If we have only one bonded to oxygen, this is going to have a formal charge of -1. And if we have 3 bonded to oxygen, this is going to be a formal charge of +1. Xe, we don't care how many things are attached to it because it can go over its octet. O and F, however, need to maintain their 8 electrons. So just to make sure, let's make sure all the different electrons are fine for each atom. O has 8 electrons. Each double bond is 2. So 2, 4, and then 5, 6, 7, 8. And each F has 8. They have the 7 around them. 1, 2, 3, 4, 5, 6, and then 7, 8 is the double bond. The single bond. And Xe, it doesn't matter, like I said, if it goes over its octet, so this is completely fine. I'm wondering how many the total amount of lone pairs in the entire compound, not just on one single atom. So we're just going to need to count these lone pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this means that the answer for this one is going to be A. There's 15 different lone pairs in the entire atom. Okay? So stoichiometry, it's a chemist's favorite plant, stoichiometry. So Dylan is a broke college student that can only afford 0.000023 grams of gold. In order to make this number seem larger, he wants to convert it to atoms as the units. So how many atoms is this? So for this one, what we're going to do is we're going to get, we're going to write out 0.000023 grams of gold, right? We're then going to convert that to moles. How do we convert it to moles? We need to put the molar mass on the bottom. So 196.97 grams of Au is 1 mole of Au. We need to further convert to atoms because it's asking us for how many atoms. So 1 mole of Au is the same as Avogadro's number, 6.022 times 10 to the 23rd atoms. If you plug this into your calculator, you are going to end up getting 7.032 times 10 to the 16 atoms, which is an answer of approximately A, right? It could be slightly off, but it's close enough. 22. We need to balance this equation. Do you guys still need to see that, actually? Okay, we need to balance the equation for number 22. So we need to figure out how many are on each side of this. So first, to balance these, you need to kind of look at both sides to see what's an odd number first. And I don't usually look at O's first or H's. I usually look at things like carbons or other type of things, such as the BA in this case. So we have 3 BAs on this side, and we have 1 on this side. So we obviously know we're going to need at least a higher number on this side of some type, right? So let's start with, say, putting a higher number on 22. So we'll start with 3, because we're going to need 3 BAs on both sides, right? So we need 3 BAs on that side. We now have 3 BAs on the opposite side. Next, we need to make sure that the PO4s are matching. We see on the right side that we have 2 PO4s. However, on the left side, we see that we only have 1. So we need to at least times this by 2, right? Now, we need to make sure that everything else is completely fine, or else we might get this wrong. So let's look at number 3. We have how many oxygens and we have how many hydrogens. So if you look at over here, 3 times 2 hydrogens is going to be 6 hydrogens. Remember that this whole thing is times by 2, not just the H, not just the O, the whole thing. So we have 6 hydrogens over here, and we have 6 from this, 2 times 3. So that's plus 6 more, which is 12 hydrogens. So if we have 12 hydrogens in the compound, how many do we need over here for H2O? 6. And BA3, PO4, too. We have the same amount of BAs on both sides, right? The PA, are the P's matching up? The PO4s? The PO4s are matching up. And just to make sure, let's make sure the O's match up with the H2O. We have 2 times O, so that's 2. And then you have to times that by 3, which is 6 O's. So 6 O's on the left side on this compound, 6 O's on this one. We have 8 O's over here, and we have 8 O's over there. So the correct answer for this one is going to be B. Okay? So step by step, work from one to the next until you get it right. So we have that formula. We have 4.2 grams of O2 reacting with 0.8 moles of CH4. How much H2O is made in grams? So to do this, we need to figure out what our limiting reagent is. So I'm going to put 4.2 grams of O2, and I'm going to convert it all the way to grams of H2O. So we have 32 grams of O2 is 1 mole of O2. This is the molar mass of O2. We then have 1 mole of O2 is the same as 2 moles of H2O. We got this because this formula has 2 H2Os in it. It does not have 1. So 2 moles of H2O. Each one of these moles has 18 grams. 18 grams of H2O. This is going to equal, if you plug it into your calculator, 4.725 grams H2O. Next, we need to plug in what O2 would do. So we're going to have CH4. So we have 0.8 moles of CH4. So that's moles. We know that 1 mole of CH4 makes 2 moles of H2O. And we also know that 1 mole of H2O is the same thing as 18 grams of H2O. This, if you multiply it out in your calculator, is 28.8 grams. Now, looking at these, we can tell that this one's smaller. So this is going to be the answer because this is the limiting reagent. So whatever's closest to that number, we see that D is the right answer. Okay. 24. 18 grams, sorry, 18 grams. This is the molar mass of water. So we converted from 1 mole of water, I should write that, to 18 grams of H2O. So for 24, 24 is another balancing one. Let's see how good you guys have gotten at this. So step by step, we're going to go one at a time. So because of how obnoxiously big number 1 is, I'm just going to leave it at 1 at first. And if we have one of these, that means we're going to have 3 of this because we have 3 carbons, right? Always wait to do O last. And the reason I wait to do O and H last is because O can usually be manipulated and changed because O2 on this can be changed around a lot. However, this is such a big molecule, I don't really want to deal with it. So if we have 1 here for H8, so we have 8 H's, how many H2Os are we going to need? We're going to need 4 more. My final question is, what are we going to do with the O2? So to balance O2, we need 4 oxygens plus 6 oxygens. That's 10 oxygens. That means that this has to be 5, making B the correct answer. Okay. Now, number 24, oh, before I even begin with 25, this was actually another error on my part. 25 is supposed to say 4.7 here. Anyway, using the equation from number 24, calculate the amount of atoms of H2O that are formed from 8675309 micrograms of C3H8 reacted with excess O2. So because it says excess O2, we know that we don't have to worry about O2 as a limiting. So we have 8675309 micrograms of C3H8. We need to convert that to grams. So how many micrograms are in 1 gram? We have 1 times 10 to the 6 micrograms in 1 gram. And this is all of C3H8, C3H8. Now that we have grams, we need to convert that further into moles, right? So we have how many grams are in 1 mole of this? So we have 44 grams. C3H8 is 1 mole of it. C3H8. We now need to convert this into the amount of H2O, right? So for every, we're going to multiply that times 1 mole of C3H8 is how many moles of water? It's 4 moles H2O. For every 1 mole of water, we have 6.022 times 10 to the 23rd atoms, right? This is going to equal total, if you multiply that all out, 4.74 times 10 to the 23rd atoms of H2O. And that's why I said let's change D, because it was 2. You would have gotten a close answer, but yeah. Are you guys okay with that? Okay. So let's go to this. We have 26 up here. States of matter. You matter to the universe. After all, you have mass. So which gas law is this? Is my first question. This is Boyle's. Good job, by the way. So this is Boyle's, and we know this is Boyle's for the fact that Boyle's is P1V1 equals P2V2. This is just saying that we have a constant T. So Boyle's is the only one out of that list that has a T that's not actually listed as part of the law. So we already know that's probably the answer. And second, it contains the form, it says that V is inversely proportional to P, meaning that they have to be multiplied together. That's why 26 is, in fact, Boyle's law. Okay, so Dylan is reenacting Salt Bay memes to attract guys in lab. His 85 milliliter love potion contains that amount of tris and that molar amount of NaCl. Tris is that. How many grams does he need of tris to make his love potion? So I need to do tris, right? So I have 0.085 liters. I converted from milliliters to liters first, because molarity is in liters. 1 liter is the same as 0.175 moles. And 1 mole of tris, according to the problem, is the same as 121 grams of tris, which equals 1.799 grams. That's about as easy as it is. I gave you a lot of unnecessary information with the salt. So people in lab felt assaulted, and now they are salty, so Dylan was stuck doing work with acid instead. He's that amount of that molarity HCl, and he has a 5 molarity stock solution of HCl. How much stock solution does he need to dilute with water? So what I need to do is I need to do M1 V1 equals M2 V2. So I have 2 molarity of 45 milliliter. And this comes from the up here, the actual equation. We know that this is what I need, right? And what I have is a stock solution, so 5 molarity, but we do not actually know the volume that I need. So to figure this out, I just use algebra. V2 equals 18 milliliters. Easy enough, right? So 450 milliliters of a glass sample of ethanol has a pressure of that at that degree Celsius. What volume ethanol has a pressure of 44.62 torr at 25 degrees Celsius? What we need to do for this one is combine gas law. P1 V1 over T1 equals P2 V2 over T2. Now, you could use other laws, such as the ideal gas law. However, it takes too long, so we're just going to use this one. We have a P1, a V1, and a T1. We know that it's 0.45 liters is 0.3 ATM over 310 Kelvin. I got 310 Kelvin by converting 37 degrees to Kelvin. And that's going to equal 0.0587 ATM times V over 298 Kelvin. If you guys find V from here, you're going to get V equals 2.21 liters. However, if you notice, my answers are not in liters, they are in milliliters. So to convert this to milliliters, you just have to move over the decimal point 3 times. Okay? Number 30. 30 is, we have, Dylan's in the zone, the ozone. Sample of ozone O3 was collected by displacement of water. It occupied 350 milliliters at 27 degrees Celsius. Barometric pressure is this. And the volume of dry, what was the volume of that dry O3 would occupy at STP? So beforehand, it's in a specific location with that pressure, that milliliter amount, and that degree amount. So these all sound like P1, V1, and T1. And we're looking for after when it's at STP, which is going to be V2 and T2. This is another combined gas law type problem. So over here we have 730 torr. I got that from 757, which is barometric pressure, subtracting 27, which is the pressure of H2O. This is going to get me the pressure of just the O3. So this is the total. This is H2O, and this is O3. If you remember Dalton's law of partial pressures, you know that if we get the total minus whatever's left in the container, we can get O3. Next is V1. We have 350 milliliters, which is stated in the problem, and T1, which is 300 Kelvin, because we can convert 27 degrees to Kelvin. P2, V2, and T2 are STP, according to the problem at STP. So we know that this is 273 and 260 torr. We have no idea what V2 is. So we have to use the same formula as before. And if you plug in all your values for P1, V1, T1, and P2 and T2, you're going to get a milliliter amount of D, which is this. You would just plug it into this equation for these numbers. Okay? Doesn't matter. Let's move up to redox. Oxidants happen sometimes. I've been having a lot of oxidants with this study union. So let's go to 31. We have where am I at? Doesn't matter. Okay. So which is oxidized, which is reduced? So to understand this problem, we need to understand what reduction means and what oxidation means. what makes something an oxidizing agent and what makes something a reducing agent. So to distinguish between these, we need to know some definitions over here. So I'm going to draw this out. I remember it by Leo Gurr. So Leo Gurr, because Leo the lion lose electrons is oxidized and gain electrons is reduced. I know some other people use like oil rig, things like that, which is just the same exact thing, but it's written in a different way. Like oxidized is loss. That's like oil rig. But I use oil rig, Leo Gurr to remember mine, because these seem to be a really confusing topic for a lot of people. So yeah. So for 31, what we're going to do is we need to see this equation and figure out what happened to the charges. What happened before and after with their specific numbers. So we're going from, I'm going to write it actually over here. So we have 2Al plus 3Cu2 plus is going to make 2Al3 plus 3Cu. What we're going to do is we're first going to figure out the charges. So this has a charge of what? 0. Al is neutral because it's in its neutral form, just in nature. And we're going from Al that's neutral to Al3 plus with a charge of plus 3. If we went from 0 to plus 3, what happened? Did we gain electrons or did we lose electrons? We lost electrons. So if you lose electrons, it's oxidized. This means it's the reducing agent. Whatever is oxidized is the reducing agent. Whatever is reduced is the oxidizing agents. Remember that they're actually opposite. I know a lot of people get confused on what an oxidizing agent versus reducing agent, what's oxidized versus what's reduced. So pay close attention if you're still confused about that. So we now have Cu2 plus, and we have Cu on the left side, which is just regular the way it is. So Cu2 plus has a charge with 2, and Cu over here has a charge of 0. So we went from 2 to 0. What happened? Did we gain electrons or lose? We gained electrons, which is reduced. If you reduce something, that makes it your oxidizing agent. So now that we worked out what was reduced, what was oxidized, the oxidizing agent and the reducing agent, we need to figure out, okay, which one is which. So the answer for 31 is going to be what? Is Al actually being oxidized or reduced, or is the Al3 plus being oxidized or reduced? So what's happening is, if you notice, the reaction's going towards the right-hand side. So whatever is being oxidized or reduced is going to be on the left-hand side. These are the things being oxidized and reduced, because they're the reactants. So what is being oxidized? What's being oxidized and reduced is the answer C. Right? Wait. Is it right? Yeah. Wait. Which is oxidized? Yeah, Al is oxidized. I don't know why I just took a pause there. So Al is oxidized because we went from 0 to 3, as we explained before. This was the reducing agent. This was oxidized. This was not oxidized. This is just the product. Okay? This is not the reducing agent itself. This was the reducing agent. So understand the difference between that. This is what was oxidized in the reducing agent, not the actual products. Same thing for Cu2 plus. This is what is being reduced, not this. This is not. This is a product of the reaction. So number 32, what is the oxidizing agent? So yet again, we're going to draw out our little formula and figure it out. So we have Cl2 plus, Cl2, plus NaBr. This is going to create NaCl and Br2. So what we're going to do now is we need to figure out where the formal charge, like where the charges went from. And so we started with Cl2. This has a charge of what? 0. It has no specific charge on it, right? However, if we look over here, this Cl is now -1. On the left side, we have Na with Br. Na has a charge of 1. Br has a charge of -1, right? What about this Na? Is it going to be positive or negative? Positive 1. And we have the Br2. The Br2 is going to be 0, because there's no specific charge on the Br2. So beforehand, we had a Cl2. It went from 0, and it changed to -1. So to go from 0 to -1, what has to happen? You have to gain electrons. Gaining electrons means it is reduced, making it the oxidizing agent. I know that pretty much answers our problem, but we're going to keep going to explain the reducing agent as well. So if we look over here, what is the actual reducing agent? So NaBr is going to be the reducing agent. What is being reduced? We're going from NaBr to Br2, right? So this Br was from -1. This Br is to 0. That means that we lost electrons. It's oxidized, making this a reducing agent. I know that's not the actual question because it's just asking what the oxidizing agent is, but I figured I would finish it off for you anyway. So 33. What is the oxidation number of S in SO2? So in order to figure out the oxidation number, we need to figure out the other charges of what's involved in this molecule. So by nature, O's are almost always -2. Okay, so Cl2 has no charge on it currently, right? Now, in this molecule, however, we have a Cl that has a -1 charge. So what happened to make this Cl negative? You had to have gained an electron. Gaining electrons means it's been reduced. Whatever is reduced is the oxidizing agent, making Cl2 the answer. Are you still confused? Okay. So oxidation numbers. If you guys forgot how I've been doing the oxidation numbers this whole time, what we're figuring out is, even though this is getting blurry again, okay. So O typically has a charge of -2. This is not always the case. Things like peroxide, for example, do not have a -2 charge. However, for the most part, O is almost always -2. Hydrogen is usually +1, pretty much 100% of the time, I believe. So if O is typically -2, and we have 2 O's, what's going to be the charge on that S? We're going to have 4. Because we have 2 O's, 2 times -2 is -4. This means that S has to be 4 in order to compensate for that -4 charge, making the answer. Mm-hmm.
O2 is by itself, it have a charge of 0, correct?
Yes, so O2 just has a charge of 0. Careful. Okay, awesome. The one exemption I can think of is peroxide, which is you're probably never going to encounter, but that's the only time where something would not be -2. It would be like a half charge. I don't remember it. Yeah, but you're not going to encounter it on your test for the most part. What was reduced? So we have another equation with CO3 -2 and 2 H's. So I'm going to draw it out over here so it makes it easier. Plus 2H plus makes CO2 plus H2O. Okay? So we're going from a -2 charge on this. We need to figure out all of the charges, like the oxidation numbers for this. So let's try to figure out what O's are. As we just explained a couple minutes ago, O's are almost always -2 charge. when it comes to oxidation number. So this would be a -2. So -2 is on each O, and we have 3 O's. That means it's going to be -6. So the O's together are going to be -6. Now, we have to remember that there's a -2 charge on this. That means that the C is not going to be +6. It's going to be +4. The reason is we have -6 oxygen plus whatever C's is equals -2. Carbon could be various different types of formal charges depending on what's attached to it. And being that this does have a negative charge, it was +4. It can vary. Things can take on all sorts of oxidation numbers. The one that really doesn't, though, is oxygen. Oxygen almost always is -2. And hydrogen is pretty much +1 every time. Everything else can vary slightly in what oxidation number it has, depending on what it's actually in. So we have hydrogen, as I explained before. Hydrogen is almost always +1. And as you see, it's plus up here, so it kind of gives it away. So this is a 1 charge, right? The C is a 4, that's a -2. So we're now going from the CO3 -2, and we're going to a CO2, right? So I'm wondering, what's happening here? And let's look at this one and what's happening here. So in this, we went from a C that was a charge of 4, and we went through a what? A C with a charge of 4. So my next question is, was it reduced or oxidized? If it was starting at 4 and it ended at 4, it didn't change its oxidation number. So was it reduced or oxidized? No. What about H? So this O is still -2, right? The H's are +1. They didn't change either. So what was reduced? None of them. This isn't even a redox reaction. So be careful when you're doing these questions. If none of the above is an answer, actually think of that as a possible answer choice, right? So before I go over periodic trends, if I could rearrange the periodic table, I would put U and I together. I thought that was kind of cute. I want to discuss with you guys the actual trends that occur on the periodic table individually at first. So let me draw a little quick picture. The ones that we should know. So pretend here is the periodic table. I'm a gifted artist, as you can tell. Here's our periodic table, right? So, oh, can't forget the intertransition metals. So, the periodic trends. So, as you go towards the top right corner of the periodic table, what happens? Well, so electronegativity increases. What does electronegativity mean? So electronegativity is the willingness of an atom to want to take in electrons. So atoms such as O are extremely electronegative. They really want to take in those electrons. Same thing with things like N, for example, or F. Actually, all the halogens pretty much want to take in electrons. Another thing that increases as you go to the top right corner of the periodic table is ionization energy. What's ionization energy? So ionization energy, in effect, is how much energy it's going to take to make this into a positive ion. So if we took F, for example, it's going to take a huge amount of energy to make this positive, right? This does not want to happen in nature. Ionization energy is pretty much saying it's going to get really high as you go towards the top right because those molecules don't want to lose an electron. The opposite of that would be electron affinity. So electron affinity becomes more negative as you go towards the top right part of the periodic table. So that would be it is increasing as you go to the top right, but it's increasing in a negative direction is the best way I can explain it. What I mean is F, when it gains an electron, right, and becomes negative, it's going to release a huge amount of energy when it gains that electron. In nature, what is it if something releases a lot of energy and it is going to be a negative joule amount? This is also known as exothermic or endothermic. This is exothermic. This is the reason why electron affinities are typically negative. It's the fact that they want to gain electrons on this side of the periodic table. And they're going to release a lot of energy when they gain that electron. Now, molecules over here and atoms over here do not want to gain an electron. Things like Mg want to lose an electron. Mg does not want to gain an extra electron. So it's going to be very difficult. It's going to require a lot of joules. This is going to be positive. Things in nature that are positive are not favored, versus things that are favored in nature, which are going to be negative. So continuing our trends, if we go the opposite direction, so if we go from the top right side of the periodic table to the bottom left, I'll draw it over here. So here's my periodic table again. Okay. What happens if I go the opposite direction? From the top right to the bottom left side of the periodic table. A couple things are going to increase. So metallic character is going to increase. What does metallic character mean? So metallic character increasing means that the thing is going to become more ductile, so it's able to be moved, it's malleable. It can conduct electricity better. This is the reason why the periodic table, the middle is called the transition metals, while the right is called the nonmetals. And the stair-step line is the metalloids. So it's important to know which parts of the periodic table are which. And we're going to go over questions talking about that later. So metallic character increases as you go towards the bottom left side of the periodic table. Another trend that increases as you go to the bottom left side of the periodic table would be atomic radius. So increasing atomic radius. Atomic radius increases as you go to the bottom left side of the periodic table. And the reason behind this is whenever you go down a row of the periodic table, down a period to a new period, you're adding another S. So if I went from, I'm going to put this picture of a periodic table in front of you. If I went from RB to CS, what's happening is, remember before with the Bohr model, how we had n equals 1, n equals 2, such and such? N is representing, in a sense, this is 1, this is 2, 3, 4, etc. So by going from, say, RB to CS, we're going one more n value up. This means that it's going further out. The further out something is, the bigger the atomic radius is going to be. Does that make sense why atomic radius increases every time you go down a period? What about what? So atomic radius increases as you go to the bottom left-hand corner. So another example. So let me try to explain like F, for example. F has a very tiny atomic radius. The main reasoning behind this is electrons around F are like that, right? They want to gain that last electron. They want to gain this last spot to fill it in and finish that shell. Now, the issue with things like Na, without its final electron out here, this electron is going to go all over the place out here. Once they're together, they're kind of balancing each other. They're kind of completing that shell around it. Electrons naturally want to complete their octets. They want to become more stable. And as long as it has only one around it, Na is going to be constantly moving its electron out to try to grab onto something else. So for example, if there's a Cl over here that's very negative, sorry, let's just pretend it's a Cl. This Cl has its electrons really close. It doesn't want to lose them. This Na, however, wants to lose its electrons. So the electron's not going to necessarily be very close to its middle. So do you guys understand that electron doesn't want to stay with Na? so chances are it's going to want to be further away. Versus Cl, where the electrons want to stay, they don't want to leave, so they're probably going to be closer in. We're going to go over problems better about this later when we come to charges and things such as that. So there you go with your different trends. Another thing about the periodic table that you guys should know is the different portions of the periodic table. So this left side is called the S block. The right side is the P block. This is the D block. And this is the F block. These are the different portions of the periodic table. These represent the different orbitals. So the S orbitals are in the left side. The P orbitals are the ones over here. The D orbitals being in the middle. And the F orbitals being down here in the inner transition metals. All of these numbers I've been explaining relates back to that stuff that we covered near the beginning of the year. So do you guys remember this? Do you guys remember these numbers? These are quantum numbers. So you guys have been doing electron configuration this whole time and things like that. So if I have an n equals, say, 1, let's say n equals 1, what's L going to be? 0. What this is saying is we're in the first row of the periodic, we're in the first period of the periodic table. So we're over here in the S corner. L is saying, OK, we're in S. So this is saying S. This is saying the first period. It's almost like giving directions. N is saying the first shell, /shell, the first shell, the first period. L is saying it's an S instead of saying like it's a D or it's a P. It's an S. ML is when you take whatever this is plus or minus 0. So there's only one value for ML. It's 0. The ML represents that this one S has only one possible thing. And the magnetic spin, which is MS, is plus 1/2 or minus 1/2. The magnetic spin represents electrons going clockwise or counterclockwise. They go opposite directions in order to cancel each other out. So this is what 1 would look like. Let's look at what n equals 2 would look like, for example. Move it down a little bit. And MS, magnetic spin. So cursive L would be what? We can have it as 1, or we can have it as 0. Either one of those values work. The reason is this is saying we're in the second period, or shell. Shell. This means that we can have an S, or we can have a P, the 1 representing P, the 0 representing S. And the ML is representing the individual orbitals. So we can go -1, 0, +1. Now, the reason behind this, and I'm using 1 for this. So this is saying that the P for 2P has 1, 2, 3 possibilities. It has -1, 0, +1. So these are kind of like directions for electron configuration. And then finally, you have the plus 1/2 and then minus 1/2. And you guys know that's the electrons going up or down in electron configuration. Okay? Is anybody confused about magnetic quantum numbers? Things like that. They're really just instructions. That's about it. So let's keep going over questions. Dylan is ready to bling himself out, but he needs the most metallic metal he can to look good. Which element is most metallic in order from least to greatest? So looking at these, we're going to look at a periodic table to kind of compare. So let's find each one of these. I'll move this up on a periodic table. So let's locate them. Ca is going to be located over here, right? We need phosphorus. P is over here. We need Cu, H, Cu is over here. H is down here. And Ra, which is down in this corner. So my question was, we need to rank them in order of increasing atomic character. Now, be warned, okay? Wait, well, actually, what did I say? Decreasing? From least to greatest. So we need the least metallic first. Now, it looks like hydrogen is very metallic since it's close to the left side of the periodic table. But this is not true. Hydrogen is extremely non-metallic. It's actually located technically in this corner. If you ever noticed on periodic tables how they write it up here sometimes, hydrogen is not metallic whatsoever. And even though it looks like as you go towards the bottom left-hand side, oh, things become more metallic, this does not apply in the case of hydrogen. Hydrogen is one of the most non-metallic elements there is on the entire periodic table. So hydrogen would be our lowest, our least metallic. So I'm going to write it up here so I remember. What would come next? So following the rule of the right-hand side all the way to the bottom left, we see that P, we see that P is located closest to the top right corner, so P is going to be next, phosphorus. Now, this makes sense because phosphorus is a nonmetal, and nonmetals aren't going to be very metallic. The next one would be Cu. Cu is located closer to the top right side of the periodic table. Now, I have a question for you guys. If we included, let's say, Si or As, would they be, okay, so let's look at these, for example. Let's compare these three. Which one of these is most metallic? Ge, because it's closest to the bottom left-hand side of the periodic table. What I want to warn you guys about, though, is remember that metalloids are half metal, technically half non-metal in a sense. So things like B, Si, Ge, As, Si, Te, Po. Po is technically a metalloid. Metalloids are slightly more metallic than nonmetals. So if you had to choose between, say, like two elements that are very close to each other, if they're on the stair-step line, they're going to be more metallic than, say, a nonmetal. Okay? If that makes sense. Like, because I know sometimes you get questions where there's like two right up and down from each other. If there's a metalloid right up and down from like, okay, so like, let's take, for example, Al versus like Ga. Al is not a metalloid. Okay, these are both metals, but this one would still win as most metallic. It's still following the rule towards the bottom left-hand corner. I don't know. I had a question in tutoring once about somebody not understanding. Metalloids are technically half metal in a sense. They're not fully metallic. They're not necessarily non-metals either. They're kind of in between. So we have H, P, Cu. What's going to come next? We have Ca and Ra. Ca is going to come next. Do you guys know what it's called, what this group is called, the second group of the periodic table? So we have the alkali metals, and then we have the alkaline earth metals, right? It's important that you guys know the names of the different parts of the periodic table. This is the noble gases, for example. These are the halogens. And they don't really go beyond that, but if you guys were curious, they're called the pnictogens, P-N-I-C, pnictogens. But they don't usually go that far. So over here, Ca versus Ra. Ca would be next, and then finally Ra would be the most metallic. The reason Ra is closest to the bottom left-hand side of the periodic table. Okay? The only reason people normally get this wrong is the H, because people think that it's super metallic, but it's not. Okay? So the answer for that one, if we go back to this, would be B. Okay? Okay. I'm going to keep going. So, which has the largest ionic radius? So to figure out the size of an ionic radius, we need to look back at the periodic table to see where the heck these things are even located. So I'm going to put this down here. It's easier to see. No, this is actually really hard to see. Okay. Okay, that works. So to figure out what the largest ionic radius is going to be when you have compounds or atoms that have a negative charge or a positive charge, we need to start thinking about this. Protons are positive, right, in the nucleus. You have electrons out here that are negative. Electrons are trying to move this way. They're trying to move towards the outside of the atom of some type, right? Sorry. Electrons are trying to go outwards. P are trying to pull them in. The positive is trying to pull the negative in. The negative is just trying to move away. Electrons are trying to go out. So normally, these are both equal to each other, right? It's kind of like a tug of war. If we have 4 people pulling in towards the center, and we have 4 people pulling out towards the outside, they're going to kind of get stuck where they are, right? They're going to be stuck in that shell. However, if we still have 4 protons and we increase the electrons, it's kind of like adding one more person pulling towards the outside. The more you add towards pulling towards the outside, the bigger the radius is going to become. Does that make sense to everybody? The more electrons you add, the more they're going to be pulling out towards the outside. And the less protons are going to be able to counteract it by pushing them back in. So for SE, for example, we typically have 34 protons in SE. SE has 34 protons. And we have 36 on the electrons. So pretend these are electrons. We have 36 of these. Now that means that there's 2 more electrons pulling out than protons pulling towards the inside. This is going to make it bigger than it normally is. So we know that SE negative 2 is going to be even larger than it typically is. Negative ions are usually bigger. Next, Br minus. So the difference between Se and Br, so Br minus is going to have 35 protons, right? And there's going to be 36 electrons out here. So the difference between these two is this has 1 extra person pulling towards the outside than this one. This makes this one slightly larger just by 1 extra electron. So Br did not win. Next, let's look at the positively charged ones. So Rb plus. So Rb, rubidium, has 37 protons. So 37 protons on the inside. Now, because it's positive, that means we have 1 less electron on the outside, making it 36 electrons. This means that there's 1 less electron pulling away than normal. So this is actually going to be closer to the nucleus than a typical. So this is going to actually be smaller than all the other ones. This is not the answer either. The same thing is going to happen to Sr2 plus. When you have Sr2 plus, what's happening is you're getting away 2 extra electrons from pulling out. So if you have 38 protons in Sr2 plus on the nucleus, you're going to have 36 electrons trying to pull away. Because you have 2 extra protons pulling in versus pulling away, this is going to be even tinier. It's going to go towards the nucleus. This one's also going to be smaller. So Se is going to be the largest. The more electrons, the more negative something's going to be, the larger it's going to be. Also, you guys have to pay attention to the fact that these are all isoelectronic. Isoelectronic means that all of them have the same amount of electrons. So Se negative 2, Br negative, Rb plus, and Sr2 plus all end up being isoelectronic with krypton, Kr. Now, if this was different, say if we included something that included like Ne, like let's say we had F minus. F minus would be even smaller than the other ones because of the fact that it has such little electrons. So don't think just because I include like F minus in this question. Remember your trends, right? F minus, F has the smallest atomic radius, right? F has a smaller atomic radius. So this is going to be smaller automatically than any of these are going to be. Okay? So first, make sure that they are actually isoelectronic before you compare them. And second, you should know that positives are going to be smaller, negatives are going to be larger. The reason you have more electrons pulling away than you have protons pulling towards the inside. What is the electron configuration of vanadium-3? So if you guys forgot, when you include a number on a atom, like an atom's name like this, you're saying that that's an ion that's 3 plus charge. So it's the same thing as saying vanadium with a 3 plus charge. So vanadium 3 plus, let's look at our periodic table again. Vanadium's over here in the periodic table. So if we're going to take away 3 electrons to make it positive, what are we going to do? Are we going to take it away from the D, or are we going to take it away from the S? So let's think of vanadium. Vanadium, I'm going to draw a picture somewhere. Vanadium, let's draw its normal electron configuration. So we have Ar, because that's the noble gas right here. And noble gas can be used in place of all the core electrons. Then we're going to go over here, and we're going to start numbering. So we have 1, 2. So that's the 1, 2, 3, 4. So that's the 4s2. We have 2 electrons in the s. Then we have 1, 2, 3 in the d. So that's 3d3. Now this is just vanadium when it has a neutral charge. However, we have vanadium 3 plus. Electrons are going to be removed from the outermost shell first. So even though I wrote it like this, the outermost shell is the 4. Remember when we drew the Bohr atom, right? The Bohr model, that n equals 1, n equals 2, n equals 3, n equals 4. The 4 is actually the furthest out compared to the 3. Electrons always are removed from the outermost first and then towards the inner. So we're going to remove these 2 first and then remove 1 more from the 3d3. So this is Ar. No 4, sorry. 3d1. No, 2. 3d2. We took 2 away from the 4s, and we took 1 away from the 3d3. This is going to get us the answer for this one, which is for number 37 as A. Now, while I'm here, I might as well mention what Cu looks like. So we all should be aware by now that copper is really weird. So copper on the periodic table looks like it should be, see number 29, copper. It looks like it should be 3d9. However, it's actually 3d10. So copper is an exception to the rule, as well as chromium. So it's important to know these two. Copper is going to be Ar along with 4s2 and 4s1 and 3d10 for copper. Copper and chromium both have this, where they take 1 away from their 4s and they add 1 to their 3d. That's why I think it's important for you guys to look over copper and chromium, because they're typically always asked. There's only 1 in the 4s, and there's an extra 1 in the 3d. This happens with chromium as well. So those are the 2 that have exceptions, and they're almost always a question, because everybody forgets this. Okay? So where is uranium found besides Cold War Russia? So we went over this before. We have the S block, the D block, the P block, and the F block. And uranium is found in the inner transition metals. We can see that over here, right? 92. This is part of the F block because it's an inner transition metal. So the answer to that one would be A. Okay. So number 39, which has the highest second ionization energy. So to figure out what ionization energy is, we need to understand what the heck ionization energy is talking about. So ionization energy is how much energy it's going to take in order to make this molecule, say like a, let's use Mg. Let's just use Mg because it's right here. It's how much energy it's going to take to make this, into an ion that's positive. So we're taking away an electron. If you wanted to write this in equation, it would be something similar to first ionization energy, and we'll use Mg as an example, is Mg plus E. Mg plus E. That would be the first ionization energy. If you notice, the electron is on the right side of the equation, and a new positive ion is formed. The second ionization energy for Mg, because I'm already doing it, is going to be Mg plus going into Mg2 plus E. So this doesn't take a lot of energy to do. The reason it doesn't take much energy to do this is because Mg wants to become positive, and it wants to be +2. There's no big issue here. Now, it does take more energy to remove the second one than it did the first, but this is very favored by nature itself, so this is not going to be our answer. Mg wants to lose 2, so we don't have to worry about that one anymore. Let's look at Al. So Al, I'm going to draw down here. So we have, actually let's look at P, because P is A. So P is going to have P, right? If it adjusts, okay, P. It's going to become P plus E. And then second, this is the first. And then the second is going to be P, because P2 plus E. Now this looks incredibly unfavorable in nature. You don't necessarily want a P to become positive. So let's keep this. This is definitely going to cause a lot more energy than Mg. Mg wants to do this. P definitely does not want to do this. So we can eliminate Mg as a possible answer choice. Now, we have P. This looks like it's probably a right answer, but we have to keep going to check the other ones. So let's go with Al. The first ionization energy of Al is going to be Al becomes Al plus E. Then the second ionization energy is going to be Al plus turns into Al2 plus E. Now, this is favorable because Al wants to become a positive ion. So this is not going to require very much energy. Yet again, I'm going to state this though. This step requires a lot less energy than this one, but regardless, this is favored by nature. This is not going to be the answer. It wants to become positive. So Al is not going to be the answer. So let's look over Na. So the first ionization energy for Na is going to be Na becomes Na plus E. And the second ionization energy for Na is going to be Na plus makes Na2 plus E. Now, let's focus on P versus Na. So Na usually wants to lose its electron, right? So the first ionization energy is incredibly favorable. There's no problem there. But once Na has lost its electron, it's acting almost like a noble gas, correct? It's acting like Ne. So by losing an electron, it's almost acting like a noble gas now. Does a noble gas want to lose an electron? No. Na in itself has a full octet of electrons. Any attempt to try to remove an electron from a noble gas type thing or something with a full octet of electrons, it's going to require a huge amount of energy. So even though P looks like it's very unfavorable, and it is unfavorable, P does not want to become positive, it's still easier to remove an electron from something that doesn't have a complete octet versus something that has its complete octet. Na does not want to remove its second. It's not going to. It's a noble gas in a sense. So this is definitely the one that has the highest second ionization energy, making the answer to this one D, not P. Now, if they did ask for the first ionization energy, which one was highest, P would be the answer, but it asked for the second, so that's why D is the actual answer. So my last question is, what is the correct electron configuration for molecular ion N2 plus 2? So understand how to do these. We need to remember our little stair-step thingy, if you guys remember it. It's when we have 1 sigma. And we have like the S, and then we have sorry, it's pi 1s, pi anti-bonding 1s, pi 2s with its thing, anti-bonding, pi, oh yeah, I keep saying pi, it's sigma, 0, 2, and so on and so forth going up, right? So what is the correct electron configuration for the molecular ion N2 plus 2? So to figure this out, we're going to need to fill in those stair-step lines, figuring out the anti-bonding and the bonding electrons for N2 plus 2. So let's do this on this paper. So N2 plus 2. First, to do this, we need to figure out how many electrons total this molecule has. So how many electrons does an N have? N typically has total on our periodic table. We see that N has 7 electrons total. Notice that I am not going off of its valence electrons. I'm going off of the total amount of electrons that's in N. So N has a total of 7 electrons. We have 2 Ns, so this is going to be 14 electrons. However, because it is plus 2, we're going to need to decrease 2. So there is a total of 12 electrons. Now, we need to draw this in our little electron configuration thing. So if you guys remember, we have the thing right here. Let me try to move this around so it's easier to see. Here, trying to adjust it for you guys. So we have this, we have 1s, we have this anti with 1s. We then have 2s, anti-bonding 2s. After that, we have the p orbitals. So we're going to have to go with sigma or pi first. Pi. So I'll go higher upwards if I need to, but so far we're going to work with these. So we have 12 electrons for N2. So we're going to start filling in from the bottom to top. Remember, guys, that actually, let me ask you guys this question. In electron configuration, there are 3 rules. Remember, there's Avogadro's. Sorry, not Avogadro's. Aufbau. Aufbau is when you start at the bottom. So you start with 1s, and then you work your way up to 2s, then 2p, etc. That's Aufbau. Because it would be Aufbau, if you started at the top and then worked down. The second one for electron configurations is the Pauli exclusion principle. Pauli is a very positive person, so you can't have 2 Paulis in a room or else they'll argue with each other. So that's Pauli exclusion. And finally, the third rule is Huns. So what happens when you put hounds together? They attack each other, right? So pretend this is 2p. You need to put the hounds separately first before you put them together. This is Huns' rule. That's the way to remember it. So the same rules apply to this. We're going to put in 12 electrons starting from the bottom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. Now, my question, now that we have a picture here of what N2 2+ looks like, we need to go back to this. Now, do any of these answers have the same configuration? Well, this part is correct for 3 of them. This part is correct so far. We have 2 for each. This represents the amount of electrons in each one. So these are all right. They're all exactly the same for the first 3. So we need to start looking at the antibonding sigma. These are all the same for all 3, so who cares there? But this is when things start getting weird. We do not have 4 electrons inside of a 2p. This does not happen. If you notice over here, we started with pi first. We did not start with sigma first. And even if we did start with sigma, a sigma bonding can only have 2 electrons in it, never 4. So we know that A can't be the right answer. Next, B. B starts with pi, right? But it goes overboard. Now it has antibonding sigma. There's no antibonding sigma to P, I mean to S, right? Oh wait, there is, wait. What? Okay, if you notice on this one, this is written twice, making this not the right answer, because you do not have two antibonding 2S's. Finally, let's look at C, if C will do the right answer. There is only one electron listed, and it's in the antibonding P. If you look at our picture, we don't even have an antibonding pi in the 2p, so C is not the answer either. So the answer would be none of the above. Okay. One more quick thing that I want to cover, because I didn't actually mention it in my section. I want you guys to remember how to do significant figures, because sometimes they will have questions that are only separated by like one number off, and it will be chosen by significant figures. How many significant figures does that have? 4 significant figures. Just making sure you guys understand that these O's don't actually count. They're placeholders. They're not actually significant figures. However, if I had 0.0302, this one has 3 sig figs, because all 3 of these count as significant figures. It's kind of important you guys look that over just in case. A lot of times they'll have 2 very, very close numbers together, and they will not necessarily be equivalent. So now that I have time left, I added some extra minutes on the end in case you guys have extra questions. I also want to make sure that I give you guys a specific paper before you leave. So before I do anything else, do you guys have any specific questions on questions? Is there anything that you guys are still iffy on that you would like an example of?
Can you go over
Number
number 2 again?
2? Let me get to it. If I can find it. Okay. So just showing you guys. Okay. I know this one was written wrong, so let me just draw it out for you. Shortest wavelength means that it had the highest amount of energy, right? Highest amount of energy is C because it fell the longest distance. So to remember, shortest wavelength is lower the wavelength, the higher the energy, and the higher the frequency. And the more it fell. Okay. Also remember that if an electron goes from N1 to like N3, it's actually gaining energy, it's not losing it. So they might have a question where they go from like N1 to N6. That's actually gaining energy, not losing. Okay. Can you repeat that? I'm sorry. Yeah, I could include one of those. That might take a long time though. A question I have before you guys all leave, I actually have something for you guys to fill out really quickly. So if you guys can grab these. Before you leave, I have to do surveys for you guys. So I'm going to be passing this out. I will cover individual questions afterwards if you guys need it, but I need to make sure you actually do these. So take one. Thank you. If you could just pass these around while I'm talking, so that way I can cover your questions and get this done at the same time. I also wish you guys good luck on your final exams.
Question. Do you still have a copy of like
That's online.
oh,
I'll tell you the site in a second. If you can, did I give you 2?
think you gave me
Yeah. Oh, yeah. There you go. Thanks. Thank you. You guys get to be brutally honest now. No. Unless, wait, let me check. No, you don't. You just need to give it back to me then when you're done. If you guys still have questions, I'm still here so I can answer them. Does anybody have any specific questions about the ACS?
Okay, I noticed
Yeah.
he didn't use like a lot of like energy examples at all. Like, do you think he's gonna?
So if you notice when you guys were doing your ACS booklet, there's barely any questions dealing with that first chapter you guys learned in Patino and Dixon's about energy and wavelength and such things like that. They don't typically ask you heavy math questions like that. Even when you went through your ACS guide, did you guys ever see any like that? Not really. It's not a commonly included thing. But if they do include it, when they give you the ACS, they give you constants up here in case you forget some things. And this is in your ACS booklet, so yeah.
Go ahead.
Oh, I was just gonna ask if on the ACS, is there gonna be like the electromagnetic radiation equations and stuff like that? Do you know?
Not okay. So I can't guarantee anything, obviously, because I don't know exactly what they're going to ask. But I can say they don't usually include a lot of math problems when in regards to physics, which is that chapter really with wavelength and frequency. But they do want you more to understand the concept. So the Bohr model type questions to understand, like, if energy is increasing, what's happening to wavelength? Or which one has the highest wavelength? Radio waves, microwaves, infrared, things like that. The more conceptual side is typically what the ACS covers. Now, that doesn't mean by any means that that's the only thing they're going to cover. But, yeah.
They don't give us any equations like this in my
They do not give you equations. They just give you this. Depending on your teacher can often give you extra stuff too. I know Patino has extra gas law questions on his, and I think sometimes like he'll include like the R value listed there and things like that. I think Patino is also including solubility rules on his thing. He did last year, but I don't know if he's going to do it this year.
No, he's gonna probably put Orgo.
And there's gonna be some.
Dixon might put Orgo on there because he did go over a chapter. Patino's is not because they never went over that. So just figured I would mention that stuff. Any other questions dealing with your final?
Okay, so I did ask Dixon about the solubility. He said he wasn't gonna give it.
Okay.
I think he'd probably give us questions then based like, do you think the ACS gives a lot?
The ACS does give a couple questions dealing with solubility, but they're not huge, major questions. You get what I'm saying?
So you
They're
can
probably like assume.
A lot of it you could pretty much figure out. If they can dissociate into ions, typically it's a salt that can, like, know the difference between what like a salt is
Yeah.
versus like something else. You know? Okay. If you guys could put all of the sheets when you're finished, I'm going to actually have a pile near the doors, and I can collect them. One pile near that door, one pile near that door.
I have one more question.
Go ahead.
For like, okay, so let's say you're talking about the metallic thing. Let's say it's between AS and SI. Like, which one would be more metallic? Like, how would you know?
Okay. Well, when it comes to this,